I have the pleasure to introduce Bridget Deveney, R&D Director at Vianova, and she will give us an explanation of how this new graphite works and the benefits of it. So please.
Yeah, thank you very much for having me here and coming out on a rainy evening to learn about graphite. So I'm going to talk about the graphite material that we produce here in the south of Norway on what is now called the Norwegian Battery Coast. To start, just a little bit about the company that I work for, Vianode. So we deliver sustainably produced battery materials, mainly for the electric vehicle industry, which is a growing industry in Europe. So we are owned by a trio of Norwegian companies that many of you, if you work in the sciences, have heard of. Elkem, so one of the leading producers of advanced materials, more than 100 years of history of production in Kristiansand. Hydro, so also extremely large company with many years of experience in the aluminum industry and other industries. And Altor, who is an investment company here in Norway. We were founded in 2021, where we came out of Elkem originally. I moved here to Norway in 2018 to work for the company on this project. And then the project became a division of Elkem, and then the division of Elkem became its own company. And now we are building a large industrial plant here in Norway. So we are scaling up our graphite, and starting in 2024, we'll be making enough graphite for 20,000 electric vehicles a year. And then in 2026, enough for 2 million electric vehicles a year. And then after that, only increasing, which sounds like a lot until you think about how many cars people buy every year, which is a lot more than 2 million or 4 million. So we are headquartered in Oslo. Our research site and pilot plant are in Kristiansand, and we are building our industrial site in Porsgrunn at Herøya Industrial Park. Right now, it says it's from September, so it says 60 employees, but we're actually around 75 now, and growing every day. So if we look at our market and why are we building our company, I don't know how many of you know very much about the electric vehicle market in Europe, but it is growing like crazy. If you look at the number of companies that are building gigafactories in Europe in order to produce batteries for electric vehicles, it seems like every week you get a new one announcing that they're going to build a giant factory. And we see that it's expected that by 2030, there will be greater than 2,000 gigawatt hours of battery production in Europe, which is a tremendous amount considering the current production, which is quite. So if we talk a little bit about the science of lithium-ion cells, I don't know, how many of you know how a lithium-ion cell works? Okay, so we'll go through kind of the basics a little bit, because it's important to understand why graphite is important for the EV industry. You need to know why lithium-ion cells work and how they work. So a lithium-ion cell is an electrochemical energy storage system. That means that you are using a chemical reaction in order to store energy. The way that you do that is you have ions moving inside of the cell that drive the chemical reaction, but you can't have any electrons moving inside the cell. In order to complete the reaction, you have to have electrons moving on the outside of the cell, which creates an electrical current. And that's how we use it to store energy, is that when you want to put energy into the cell, you push electricity into the cell and you drive the ions in the reaction direction that is not positive, or it's not electrochemically desirable. And then when you complete the circuit, you get the electricity coming out so that you can use it to drive your car or power your flashlight or any of the other things, use your phone, any of the things that you would use a lithium-ion battery for. So in a lithium-ion battery, you have two materials that are used to store the energy, where you are shuttling the ions back and forth between them. You have a cathode and an anode, a positive and a negative. For the cathode material, There are a lot of different materials that you could use. For example, people use lithium iron phosphate, or they use nickel, cobalt, aluminum, lithium cobalt oxide, nickel manganese cobalt. In nickel manganese cobalt, you can have the ratio of the metals be 1 to 1 to 1, or 5 to 3 to 2, or 8 to 1 to 1. So there's a big range of different materials that people use for the cathode. And you might hear a lot of talk about cathode materials, particularly because of the cobalt content of many cathode materials, where the largest production of cobalt is in the Congo, the Democratic Republic of the Congo, which is not exactly a great and sustainable place to be getting your materials from. So the cathode material gets a lot of press with how to get rid of the cobalt, how to make it more sustainable, how having all of those metals like nickel and lithium is very problematic. But what people don't talk about as much is that the other half of the cell, which you have to have in order to make it work, you can't run an electrochemical cell with only one material, is the graphite. And here there's not really a lot of discussion because every electric vehicle on the road is full of graphite in the anode. Every iPhone that you have, full of graphite in the anode. Every battery that you have on the road, graphite. There's not so much variation in what people actually use. So there is a lot of research on other anode materials. There's a lot of discussion on other anode materials. But if you look at commercially produced lithium-ion cells, every cell that comes out of the Tesla factory is 95% graphite in the anode. Every cell that comes out of the CATL factory that's being built in Germany is going to be 95% graphite in the anode. So then if we talk about graphite, how does it work? So this is important for understanding why graphite is the dominant anode material and why we expect it to continue to be the dominant anode material into the future. So when you charge the lithium ions into the graphite, what happens is graphite is a series of layers of graphite in hexagons that are long sheets. And then between them, you only have van der Waals bonding, so very light bonding. And it's quite easy for those sheets to separate just a little bit. And so when you push the lithium ions into the graphite, it goes between those layers of sheets and it sits right in the middle of that ring of atoms. And then that allows it to be stored in a very stable way. So what makes graphite work so well as an anode material is that you're only moving the sheets of carbon atoms a little bit apart every time you charge and discharge. And so the fundamental structure of the material is not changing. So that's what's called an intercalation material, where you can put ions into and out of the structure without changing the chemical bonding between the atoms in the structure. So when you have a material like that, it can be incredibly stable because you're not rearranging those chemical bonds. Every time you rearrange the chemical bonds in a material, you have the risk that the bonds don't go back to the way that they were at the beginning. And then that means that, even if you have 99% of your bonds go back to the way that they were at the beginning, a lithium-ion battery is considered to hit end of life when you have 30 to 40% of the capacity gone. So then you're only talking about you losing 1% of your capacity with every cycle. And then all of a sudden you're 30 cycles, 40 cycles. So you can imagine how efficient the reaction has to be in every cycle in order to get the required life that you need for an EV battery. When you buy an EV battery car, it's expected that you could charge and discharge that battery 2,000 or 3,000 times before it hits end of life, which means that that reaction needs to be incredibly stable. And that is why graphite is the dominant anode material, is because it is able to work in that way. But what we see that is exciting about graphite is that even though it seems like a very simple system where you have layers of carbon atoms all in the same structure, seems very simple. And yet it has been the commercial anode material of choice for 40 years. And we still do research on it. And we still don't entirely understand the mechanisms for storage of lithium inside the material. In fact, we have graduate students at University of Oslo now doing in situ XRD analysis for us on how you charge and discharge graphite materials to look at these different models that you see here of how did the lithium ions preferentially fill into the different layers. Because they don't just fill one next to another all crowded into one space. You tend to fill either the furthest apart in different layers or maybe in different sections of the layers. Kind of like thinking if you were trying to fill a parking garage and you wanted to keep your car furthest away from everyone else in the garage at any one point, that you would pick different spaces to fill in a particular order that would be optimal for having the most distance. So what we see with graphite is that there is still lots of exciting research to be done, and that is part of what we are doing in Vianode. If you know a little bit more about lithium-ion batteries, the next thing you might ask is that you read that silicon and lithium metal solid-state batteries are going to take over the entire industry. So why do we really care about graphite? Graphite's so old, it's so boring. No one wants to work on it anymore. People are all about solid-state batteries. But what we see is that when people talk about how silicon is the new anode material, how silicon has greater energy density, how silicon is going to take over the anode material market, what they forget about is that the way that silicon works is fundamentally different from the way that graphite works, where silicon is an alloying anode material. So if you look at the picture up on the right, you can see the structure that you get for the atoms in crystalline silicon. And then if you look just below that, you can see the structure that you have when you have fully lithiated silicon material. And you'll notice that all of those little orange balls, those are the lithium. And that's because you have, for every one silicon, you have more than 3 lithium atoms. So you have entirely broken all of the bonds between the silicon atoms, which means that every time you push all of those lithium atoms in and pull them back out, all of those silicon bonds that have been broken have to come back in exactly the same way, in exactly the same structure, in order to maintain the material the way that it was built. And that's pretty unlikely to happen. So the other thing that people talk about is lithium metal, because of course, if you want to have a lithium ion battery and you didn't have a material to store the ions in, on one side, you only had the metallic metal that you're shuttling back and forth, then your energy density could be much higher. But what we see with lithium metal is that it stores energy through what's called a plating and stripping process. It's a metal, you're just plating it on the surface and you're stripping it off, kind of the way a lead acid battery works. But lithium metal doesn't form a smooth surface when it's plated. It preferentially tends to attach to the last lithium ion that went onto the surface, and it forms this lovely tree-like structure called dendrites. And so you can see that if you are trying to keep a nice uniform structure, and instead you're getting all kinds of little tiny trees growing up into your battery, that's not a very efficient reaction that would be stable over the long term. What you do is you form lots of extra reactions on the surface and passivation layers, and eventually you start to run out of lithium metal that is available for cycling. So generally, we believe pretty strongly that graphite is going to be the anode material of the future, which is why we just invested 2 billion kroner in our first plant, and we will invest considerably more than that in our second plant. Okay. So then if we talk about where is our graphite anode material coming from now, and why is it important to be able to make it in Norway? What you can see here is a map of where in the world graphite anode material is made. And you'll notice that almost all of it is made in China. So right now, about 1% of the synthetic graphite material that goes into your electric vehicle batteries is not made in China. And even by 2030, with all of the plans for expanding production in Europe and the battery coast, it will only be about 8% of the graphite anode material that is not made in China. So that can be a concern for a couple of reasons. First is that overall, we see this massive supply and demand gap, that we see that by 2030, in order to be able to feed the European battery industry, you would have to have 1 million metric tons of graphite anode material being made in Europe, which is not very much compared to what is planned. And given the issues that we have geopolitically with China over trade, there is a lot of risk that if something were to go badly in the future or the relationship became more strained, that China could decide to cut off the supply of graphite anode material into the EV industry in Europe, or not even to cut off the supply, but if there are shortages in China, then of course the Chinese industry would be given priority to buy these materials, and then they would not be available for the European EV industry. So it's important to have localized supply of materials. So here you can see an example of what we expect to happen by 2030, that the demand will significantly outstrip the supply in both North America and Europe, but also in China, because in China, there is a significant number of gigafactories being built. So we expect that even there will be 500,000 metric tons of shortage in graphite anode material versus the number of gigafactories that are going to be built. So the other thing that we see in Europe is that EV manufacturers and the government are focusing more on sustainability of electric vehicles. You know, it used to be a few years ago that people just assumed, oh, it's an electric vehicle, of course it has to be green because it's electricity, it's battery powered, you know, of course, must be green. But people don't just take that for granted anymore. You know, we see that governments are pushing EV manufacturers to have digital passports for their batteries, to understand the CO2 footprint of the materials that they're putting into their batteries, and to understand where those materials are coming from. So here is some timeline of the EU regulations that we expect to see, or that we have seen in the past around batteries. You know, we see that by next year, or by 2024, people who are making batteries will have to actually document their carbon footprint. So you would be able, when you bought an electric vehicle, to see the sticker on the window that tells you the range and where did it come from, what is the overall CO2 footprint of your car. And that can make a tremendous difference, because if your electric vehicle was built in a country that has a lot of renewable energy, then the payback time in CO2 footprint for having built an EV versus running your car on gasoline or diesel is maybe only 2 years. But if you were to buy an EV that comes from a country that has mainly coal-fired power, then you're talking about 7 or 8 years before you see the return on that CO2 footprint. And then it becomes a little bit more problematic. So they want to push people to be able to manufacture in countries that have more renewable energy. So then your electric vehicle actually becomes green. And then we see further out into the decade going to requiring higher recycling efficiency. So you can't just throw away those batteries that have all of those important metals in them. You have to be able to recycle them and be able to use previously recycled materials. So we see up to 2030 that people will have to have a certain content of recycled material inside of every electric vehicle that they make. So then we get to the question of, why is it so difficult to expand graphite production into Europe? And the reason is because of this giant pit that you see before you, which is an Atchison furnace. So this is the technology that is used to make that 98% of graphite that is produced in China that goes into all of your electric vehicles now. It is produced in this 100-year-old technology, which is a giant pit furnace that is very open into the air. So these pit furnaces are it's a giant pile of graphite and coal, and you put electrodes into either side and just pull the electricity through the center of it until you heat the material up to the correct temperature. But what happens during that time, because it's an open furnace, is that all of the metals, all of the sulfur, all of those other elements that were inside of the raw materials that you use to make graphite come out into the air. And then on top of that, you have a lot of cover coke in order to contain the temperature and protect the material. And you have to dig that coke out and move it around every time you empty or reload the furnace, which makes a tremendous amount of dust in the general area. It's not really a green or sustainable way. It's not the kind of thing that you would want to have in your hometown and look at to think that that is necessary in order to build your nice green electric vehicle. Why do you have all these problems when you're making graphite? If we talk about how graphite is made, so when we are making synthetic graphite, we start with petroleum coke. So it's a byproduct of the oil industry. You know, after you have taken the oil out of the ground and you've taken off all of the gas and you've taken off all of the diesel fuel and you've taken off all of the heavy oils, you end up with this sticky, heavy residue at the bottom of the barrel. And that is what we use to make graphite. It's the highly aromatic stuff with all of the different kinds of materials in it. But unfortunately, because it is the bottom of the distillation process, that means that all of the metals and the sulfur and things like that that would have been in your gasoline end up in the coke. We see that over time, there have been more and more requirements around fuels that people will use for internal combustion engines to have lower sulfur content, lower metals content, so that you can make those cars greener. But you can't just make oil have lower sulfur content or lower metals content. So what happens is that that material ends up in the petroleum coke, which is what we use to make synthetic graphite. So then if you have an open furnace where you are making your synthetic graphite, all of those elements are coming out into the area around your furnace. So what we see with our materials in our furnace is that we at Vianode have developed a furnace technology that is an entirely closed furnace, so that we don't have this kind of off-gassing in the area. We see that by having this closed furnace, we are able to be much more energy efficient. So we use 40% less energy in the production of our material than you would in China. The other thing that we see is that because we are here in Norway, where we have access to green hydropower and power with a very low CO2 footprint, that overall we are able to reduce the CO2 footprint of the graphite material that we make by 90% versus what you would see coming out of Asia. So it's a significantly greener material. It's what you want to have in your electric vehicle. We also see that we can have a higher raw material efficiency, and that all of those off gases we are able to collect in a very sustainable way where we're not polluting the environment because of our closed furnace solution. We also do a lot of work on zero waste, so recycling of our anode materials, energy recovery from our furnaces, so having the high temperature waste heat go into the lower temperature processing so that you have a flow of energy through the plant and you're not always using new energy if you have to heat things up. And then we also do a lot of work on our side stream material utilization. So waste that might come out of our plant or byproducts that might come out of our plant, finding other places to use those in the process or other companies to sell those to. So if you are very interested in the battery material industry, you might also ask, well, what about natural graphite? Because of course, things that are natural are always very nice, right? It's just sitting there in the ground. Instead of having synthetic graphite that has to go to such a high temperature, you can use natural graphite. But what we see from natural graphite is that you cannot use it just from the ground. It's not like you pull the natural graphite out of the ground and it is ready to use as an anode material. It has to be chemically purified. So most of the chemical purification that is done requires a large amount of hydrofluoric acid. Because graphite is a naturally occurring mineral, it tends to have a lot of silica deposits in it, and silica is very difficult to get rid of. Really, the best way to get rid of it is to dissolve it with hydrofluoric acid. So if you have worked in industry, you might know hydrofluoric acid. It's quite nasty. It is a weak acid, which sounds like it would be nice, a weak acid, but because it's a weak acid, it can go through your skin and into your bloodstream and cause the calcium in your bloodstream to precipitate, which can give you a heart attack. It's also extremely corrosive, bad for the environment, makes nasty hits like that. And natural graphite, it's a mining operation, generally a pit mining operation, which means that you just start at the surface of the ground and dig giant pits into the ground. So it's having a sustainable way to make synthetic graphite, even though it does require more energy than getting natural graphite. Can overall be a greener way to produce your batteries because you are able to control where that energy comes from, and you're able to control any byproducts of the process and not put them out into the environment. Okay, so I hope the Ida cluster does not mind me stealing their picture. This is the Norwegian battery coast. So many of you have probably heard of companies like Morrow. They get into the news a lot, but we have quite a few battery-related companies along the southern coast of Norway. So we have Eramet, we have Nikkelverk, we have Agder Energy, we have Morrow, we have Beyonder. But what is very nice about this and having this large cluster of people all together is that it helps us to create a kind of concentrated industry that can work together and can help to really create a circular economy of industry altogether. So because we have so many battery related companies, we are able to sponsor things like a battery education center here at the University of Agder, where people can come and learn about how batteries are made, how to design batteries, how to make battery materials. If you had just one company in the area, they wouldn't be able to afford to do things like that. And it also helps to create an overall educated workforce. You might think that it could be good to be a company all on your own so that your employees can't leave for other companies and there's not so much competition for them. But in fact, having more companies in the same industry in an area tends to make people feel like that industry in that area is a more desirable place to be because they have options for where they could work without having to move. And they have opportunities to interact with other colleagues. They have opportunities to come to discussions about their industry with people from other companies and to grow professionally. We also see that in the south of Norway, it is a very nice place to be for battery materials because of the existence of the educated workforce. We see that there are a lot of companies with experience in the process industry, not just Elkem or Hydro or Glencore Nickel Works, but companies that are very experienced in very high temperature processing and having to economically make large amounts of material, in understanding how to manage processes that have safety hazards in a safe way. And that is very important for being able to set up a new industry. We also see green power availability. So here you can see a dam for hydropower, which is very nice for us. It used to be low cost power, which we really liked, but we're hoping that it'll go back to being low cost power again. So what we see from Vianode is that we have significant external interest in the company, where we have people inside of Norway coming to visit us, but also people from the EU coming to visit us because they are very interested in the idea of Norway taking on battery production and battery materials production because of all our green electricity. If we look a little bit about where we are in the history of our company, we started out in 2018 with our pilot scale operation, which was a very small scale. So we were making around 2 or 3 tons of material a year, which sounds like a lot, but it is actually not very much at all. And then we opened our industrial pilot last year at the Elkem Fiske site. And at that pilot, we could make around 50 tons of material per year. We are opening our first production site in 2024. And there it's significantly more. And then with the very large scale industrial site opening in 2026. You can see a picture of what the industrial site will look like when it's done. It's quite a large building in order to house all of that equipment and make that much graphite. It does take a lot of space in order to produce this amount of material, which is one of the reasons why it's very nice for us to be located in Norway. And of course, if you're going to make green material, you have to have solar cells and green roofs in order to be a very green company. So one of the next things that we look at for Vianode is being able to have a more circular economy in graphite. So of course, we make the virgin graphite that we sell to people down the road in Arendal maybe, who would make it into batteries, who would sell it to people to put into electric vehicles. But then what happens at the end of life for those electric vehicles? So we look at working with companies that recycle batteries and being able to recover those materials to lower the CO2 footprint even more. Because even though right now there is a lot of available petroleum coke for us to make our graphite out of, at some point, maybe there will not be as much petroleum coke if you are good at getting rid of the oil industry. And then we have to look at other ways in order to make our graphite products. So if we look at our position in the recycling value chain and how we work with recycling, we make the anode graphite material. And then when we sell it to our customers, what they do is they take it and they make it into a slurry. So like a liquid, kind of like a paint. and they paint it onto an electrode, and then they turn that electrode into a cell. But you would be surprised at how much of that material is scrapped, particularly when you are starting up a new gigafactory. Your scrap rates can be quite bad. So somewhere between 20 and 30% of the material that we sell to our customers every year ends up just going out the back door of the plant into the trash, which is not very sustainable. And so we have started to do a lot of work with them on how we can recover that material instead of just throwing it away, turning it back into graphite material that they could feed directly back into their process, which saves them money. It's good for the economy. It's good for sustainability. Overall, good for everyone. And so we work with companies that do recycling on mechanical separation of the materials and also hydrometallurgical processing of the materials in order to recover the graphite and turn it back into the usable graphite material. And so what we see is that that is entirely possible to do. That with the processing that we have developed, we are able to take that scrap graphite and renew it into new anode material that works in exactly the same way that the virgin anode material worked, except then we're able to cut out an extra 40% of the CO2 footprint of that product, which, you know, it wasn't so much before because we've already taken 90%, but it's always nice to try to get that little extra bit at the end. And here we have a lot of very exciting research projects that we work on, funded by the Norwegian government. For example, the Green Platform project, where we work with Hydro and Morrow, Freyr, Corvus, IFA, and Sintef. So a very exciting project for us to be able to work on the next way to improve the sustainability and circular economy. And then I have a little pitch for our technology center in Kristiansand, which we just opened this year. So it's our state-of-the-art research center on battery materials, where we have room for 25 scientists. So we're hiring scientists. People are interested in coming to work on battery materials in Kristiansand. We have lots of exciting new equipment for people to work with on developing sustainable battery materials. It's a very exciting place to work. And just to give you some example of what do we work on at our technology center with graphite, you know, graphite is still a material that's in development. One of the most important features that we see about graphite is that, you know, because the potential of graphite is actually so close to the potential of lithium metal, which you can see in the top chart. As you insert the lithium ions into the graphite, the potential can get quite low and close to the potential of the lithium metal. So if you try to push the ions too fast at the surface of the graphite, you can form metallic lithium on the surface, which is called lithium plating, and it ruins your battery. But of course, everyone would like to be able to charge their electric vehicle at the same rate that they used to fill their gas tank. That's kind of the big goal for electric vehicles, is everyone wants to be able to stop by the side of the road and get out and plug the thing in, and 5 minutes later, you're back on the road with a full battery. And the graphite is the thing that is stopping you from being able to do that. So we do a lot of work in our laboratory on understanding how we could change the structure of the graphite in order to enable our customers to have that kind of fast charge rate that they're looking for. So for example, we can look at the lithium diffusion inside of the structure of the material to see if we change the crystallite domain sizes or the orientation of the crystallite domains or the sizes of the particles. How can we improve that fast charge capability? We also look on more of a production level that we see that when our customers make the coatings out of our graphite, that the graphite is particles and they are laying them down in a layer, like a particle structure, where the particles are stacked on top of each other. And so it makes a pore distribution inside of that material. And the distribution of those pores, the size of them, the ability of the ions to flow in and out of them is very important for the fast charge capability of the material. So we do a lot of work on how you could change the structure of the particles in order to make better pores with higher density that would still work very well for fast charge. So if that's something you're interested in, come talk to me about the positions we have at Vianode. So yeah, I just have a little bit more about overall for the company. You know, our goal is to become a leading company in Europe with a large amount of the market share. to make enough material for 2 million EVs every year by 2030, and to have a domestic supply chain. We want to be able to make material with long life that is very recyclable, that is very green and sustainable. We want to enable that European transition into the electric vehicle market without having to use materials that come from less desirable processing and in areas that we would prefer not to buy from. We think that it's best, if we're going to have a European EV market, to be able to have a European battery materials market that is the same level of sustainability as the cars that are built here. Yeah, that is it for me.
Thank you very much, Bridget. It was very interesting, and I think we all learned a lot about batteries. And interesting for me is that the company of Elkem, where I have worked many years, is instrumental in this development. For your last comment, we have to charge so fast that is similar to fill up with diesel or gasoline. Mm-hmm. So I drive an electric car myself, and I think it is sound to sometimes take a rest for 20 minutes, because if I earn a lot of time with charging fast, what shall I do with that time? I have to have a plan for the time you save. No, that was just a comment. Thank you very, very much. It was very nice to hear you in this speech. We have a book from our academy. It is called The Digital Weekday. Hverdag, weekday, yes. It's written by members of our academy. So this is what we have to hand out for our guests. Thank you very much. Thank you.
Tusen takk. Yes. No, we see that we're able to make graphite that has the expected properties. Yes. No, the structure comes from the raw materials that go into the graphite. Mm-hmm. Yeah, which is another reason that it can be very interesting to be in Norway, is because we use petroleum raw materials. So there are a lot of people in Norway who have experience understanding the structure of petroleum-based materials. Yeah, so it is it is possible to use lignin or other biomass to make graphitic structures. It's not very energy efficient because you have a very disordered carbon structure in those materials. And in order to make graphite, you have to force the structure to become fully ordered. So when people do that, they usually use a lot of catalysts in order to get it to work, which does work. But when you look at the amount of energy that you have to put into making the catalyst and then adding it to the graphite material, it would be more energy efficient to go from something that is already fully ordered, like petroleum coke. But there are materials that people make out of biomass or lignin. For example, for sodium ion batteries, you see people use hard carbon, and that can be made from biomass.
Thank you.
So my question is like, have you mentioned that in terms of the recycling process, normally if you see generally most of the batteries, when you do the recycling, it's only the cobalt is the one which give the economical profit for the recycling process. But if you talk about the graphite, how profitable it is in terms of as a company. And also you have mentioned it's a 99.99% of purity it is you are getting the graphite after recycling. Do you want to use the same graphite for the manufacturing once again the battery material, or it's some kind of degrading material?
So it certainly would not be profitable to recycle the graphite on its own. But what we see is that as the industry develops, it is not just the cobalt that people are recycling. They're trying to remove all the nickel and the manganese as well. And so by the time you've removed all of those materials, you end up with what is already quite a high concentration of graphite at the end. So instead of just throwing it away, we can use it to recycle it into battery material again.
Thank you very much for a very interesting presentation. I have a question related to the scalability of what you showed a gap, that the projection that even in 2030 there will be a significant gap between what China can produce and Europe and North America will be able to produce. What will prevent scaling up new solutions to close the gap? Which are the factors that limit this scalability?
So I would say the two factors that cause the gap to continue are regulations and funding. So we see that manufacturing in China is cheaper because they don't have the same regulations that we have for emissions in the US. So if the European Union and Scandinavia allow people to continue to buy material from Asia, just based on the lower cost without any requirements for higher sustainability or lower CO2 footprint or anything like that, then that makes it difficult to build a European industry that can compete. The second thing that we see is the funding. So for example, we see in the United States that as part of the Inflation Reduction Act, they have given almost $500 million to graphite companies in the past year in order to build factories in the United States, because they see that that material is critical to building the EV industry, and they believe that it should be locally sourced.
Ask one more question. In a recent PC defense, where I was opponent in Spain, where they work with circular economy, the topic was about creating industrial further licenses in a planned project to achieve the circular economy. When you look at the battery cost, as you mentioned, that is this kind of accidental that it formed, or is it a question of that the enterprises attract each other in some way, or is there a planning mechanism, an overall planning mechanism to achieve this industrial higher level of cooperation?
Oh, you know, I am not entirely sure. I guess that is a combination of both, that it started out a little bit random, that battery and battery materials production are both very energy intensive industries. And so Norway is usually very attractive for energy intensive industry because of the low power price. But then once you get a few companies in the area, it starts to look more interesting for other companies. And then there tends to be more funding available from the government that is focused at that industry. So you start to grow smaller companies and have more people available to work in the industry, more students who are working on studying it. And then it kind of feeds and grows on its own. But hopefully it will grow a lot more. You know, we see that between us and Nickelworks and Morrow and Beyonder and Fryer up in the north of Norway that we are all expecting to hire about 5,000 engineers in the next 5 to 6 years. So need a few more engineers.
And it's good that you have candidates.
Yeah, related to battery degradation life cycle, do you use any kind of like machine learning technique also to like optimize and to understand like how much battery degradation can happen in the whole life cycle of that?
So we don't do any work on the battery level, but what we do is a lot of work on modeling of our products and also modeling of our plant. So we have work on creating digital twins of our plant so that we can optimize the processing and the throughput, and then hooking that up to our testing in our laboratory so that we can do machine learning to understand the interaction of the processing parameters with the performance of the products. I guess everyone is ready for Christmas dinner.
Yes, that's why they are so quiet.